Alright, what's going on? So I'm gonna go over this problem, the daily problem for today. So unique binary search trees. Given in how many structurally unique BSTs, binary search trees that store values of 1 to n. So they give an example here. They have input 3 and the output 5. And they have 1, 3, 2, 3, 2, 1, 3, 1, 2, 3, 2, 1, 3, and 1, 2, 3. So let's look at if there's a pattern here. So I'll copy down this one. So if we're given n equals to 3, what we could do is we could say we have 1, 2, and 3. And we could say if we have one node, so let's say we start out with this node, the 1. If we start with the 1, we can then add a 2 to it, which is 2 would go over here, and then we could add a 3. Or we could add the 3 and then add the 2. So there's 2 trees here. And you might think, so okay, so there's 2 trees here. And then we go to the middle one, so we go 1, 2, 3, and we go to the middle one. And the middle one we say, since we can't like split this up, there's only one tree on both sides. And one way to think about this is, well, why is there only one BST formed on both sides? Well, in a sense, because you have only one number to the left and one number to the right. So in a sense, you could be thinking any tree that has just one node is, you can only form one tree, right? So any BST that you're forming with just one node, like just one, right? Like I guess you're just forming like a subtree. If you're forming I guess I don't know how to explain this too well, but if you have just this node 1, you can form one tree, right? And you can only have one subtree for the 3. However, over here, if you're using 1, then you have these 2 values, which are can form a binary, a BST subtree together. And you can notice, I mean, you can form 2 BSTs from this, right? Because you could go one in front, or the other one could go first. And then what you can see here is that as you're iterating through here, you're kind of like doing something. Like if you're at this 1, you know that you have this 2 nodes here, which can form 2 binary trees, right? If you're at this 2, you know you have this 1 node here and this 1 node here, which can only form 1 binary tree, I guess. And then if you go here, you have these 2 over here, which you know can form 2. So the total is you can form 5 BSTs from this. To go even more simple, or start from the beginning, if you have 1 and 2, you can kind of see that you can only form 2 binary trees. Like that. 2 BSTs, I mean, binary search trees. So you can only form 2 of them. And of course, it's following the binary search trees, how it works, where a larger value always to the right of the node, and a smaller value is always to the left of a node. In fact, any subtree down here has to have lower values than this root node. That's just like I guess a really quick review of BSTs. But if you have this 1 and this 2, so we know we can only form 2 here, right? If we have 1 node, we know we can only form 1. And now we know if we have 3 nodes, we can form 5. And then now let's think about if we have 4 nodes. Is there a way we could figure out 4 nodes very quickly? Well, there is. So think of this. If you use 1 first, and then you have this 2, 3, 4, that's 3 nodes, right? That's the same thing as having 1, 2, 3, isn't it? So you could say, hey, I have 5 here, and then say plus, because you could form 5 BSTs from this, right? And then I would say, well, I can't write it like this, and then say, so just say I have 5. And then I go to this 2, and I say, well, I have 2 over here, and I have 1 here. So I could form 2 BSTs, because 1 BST we're just going to say is 1, so we'll say 2, so I have 5 and 2. And then if I start with a 3 node as my base, I can form 2 binary search trees with this 1 and 2. Or if I go to this 4, I can form 5 with this. So the pattern is you get 5 plus 2 plus 2 plus 5, right? and you can see this is equal to 14. So now we know it's 14. And so I'm going to give a couple of numbers. So when n is 3, we have 5, and when n is 4, we have 14, and then when n is, I'm going to give the answer for this one, when n is 5, it's 42. Now, how do I do this? I need to remove all of this from my screen. Okay, I guess that's the quickest way to remove everything. So then what I'm going to do is I'm going to try this out. So what if we have 1, 2, 3, gosh, I'm really bad at writing, sorry about that. But anyways, yes, you have 1, so I'm trying to do, I have 1 to 6 nodes. So here, what we can do is break it down into a subproblem where we can say we already know, like we already kind of like keeping track. There are a number of trees for, so I kind of like create an array where the index 0 is going to be 1, and then index 1 refers to when we have 1 node, which is like 1, and then index 2 refers to when we have 2 nodes, which we already know is 2, and then the third index would be 5, and fourth 14, and the fifth 42. Following this over here, right? So that's our array. So what we could do is we could say when we start at the 1, we can form this, right? This is 1, 2, 3, 4, 5. So that's 5 values, and we know when we have 5 consecutive values like this, we can form 42 BSTs. So what we're doing is we're kind of taking the 0 index and the first index. So we kind of say how many trees can we form from the left subtree? Well, we'll say 0. We'll say there's 0 nodes over here, so this is 0 index. So we'll take some type of matrix or array, and we'll take the 0 times the, oh my gosh, maybe I should just type this. So let's say we'll take array 0 times array 5, right? So we have 42 here. And then we're going to say, that's just one of them, but then what happens when we move from the 1? Oh, rats. I erased that, okay. So we have to move from the 1 to the 2. God, I accidentally erased that. Then we have this 4, right? And these 4, and we have 1 over here. So we take, so we take array at the 1 index times the array as if we had 4, which is the fourth is 14, and the 1 is 1, so it's going to be 14, which is true, right? And I'm going to go back. Oops, it won't let me, okay. And then if we go to, wait, can I go back? Oh yeah, I can go back this far. Then we go to the 3, we have these 3 and we have these 2. So that's the same thing as taking array 2 times array 3. So in a sense, these indices values are like, based off the node that I'm at, I'm looking at how many nodes I can form a subtree on the left and how many nodes I can use to form a subtree on the right that are BS tree subtrees. And you're going to see this pattern kind of continue where you're just going to, you're going to keep taking these nodes. And in a sense, you can see the pattern like, oops, sorry, I don't know if we're going to have time. You can see the pattern like this. Let me see if I can do this. So it's going like array 0 times array 5 plus array 1 times array 4 plus array 2. I'm going to write an n, and I'm going to explain again, I guess. Maybe I'm overkilling it. I don't know. I could be overkilling it very much. So, and then array 4 times array 1. We'll stop. Oops, what did I just do? Did I just subscript it? Okay, and then array, what was it? What was I? I was at 5 times array 0. So we go back to the beginning. So you can think here, what this is saying is that this code is saying where we start at this node 1 and we have 0 nodes to form the left BST, and we have 5 nodes to form the right BST. Here we have, when we go to the 2, we have 1 node on the left and 4 nodes on the right. When we go to the 3, we have 2 nodes on the left and 3 nodes on the right. When we go to the 4, we have 3 nodes on the left Did I mess something up? Yeah, so, well, my bad. Okay, so I know where I'm at now. So when we're at the 4, we have 3 nodes on the left and 2 nodes on the right. And we're at the 5, we have 4 nodes on the left and 1 node. So you can see the pattern that basically this is like how many nodes you have on the left to form a BST subtree, and so on. So by using this, you can code. So I hope this explains the basic idea. I think I could explain a little better, but hopefully that will get so much. So let's look at the code of this. So first I'm going to do a naive approach. It's just recursion. Yeah, this approach did not work. So we'll just do recursion. So to do recursion, we're going to need a base case. So let's say if n is equal to 0, we're probably going to want to return 1. If then we want to do the recursion itself, we're also going to have to go through our, for I in range, we want to go from 1 to the n itself. And then I want to take this res and just add up the values that I get from doing the recursion num trees, and we want so the first value has to be, I said it has to start at 0, then it has to increment, right? So for it to be 0, I'd have to do I minus 1. So 1 minus 1 is 0. Then as I increments, it'll go all the way up to n equals, for my example, since I'm doing n equals 6, because I have 6 nodes here, it's going to go all the way to 6, and then 6 minus 1 is 5, so it would work. That's my left subtrees, and my right subtrees will be, oops, my bad. My right subtrees will be, they start at 5 and they decrement to 0. So for this to be 5, I need, it starts, so I starts as 1, so it's kind of like taking n minus I, and then I increments, and then n is going to be 6. I will go all the way to 6, so this will go all the way to 0. Okay, so that seems to work. And then I think I just want to turn res. Is that it? I think that's it. Let's run code. That's just the naive recursion approach. Sure, yeah, I guess I should probably reference that first. Yes, my bad. So it works for this. We could do easy inputs, let's do 10. I could do 1, too. Okay, it works. It might be a little slow. Oops, 1, I'll do 1. You can't have 0. Okay, so it accepts that, so we'll just submit it. And then we'll do dynamic programming next. Dynamic programming is not going to do a naive recursion. It will instead save the subproblems that we've already solved in an array. Oh, time limit exceeded. So apparently this is too slow using naive recursion. So we're probably going to have to use dynamic programming in order to not TLE. Okay, so let's start the dynamic programming. So to dynamic program, I need a memo table. And it needs to be 4 in range. It has to be the size of n plus 1. Yeah, so it will be from 0 to n for the indices. We're not going to need this code anymore. And then what we're going to do is we're going to fill in this thing. So we're going to need 2 for loops. For I in range of, I think, n, and then for j in range of something, I don't know. So let's just figure out what we need to do. So we're going to do memo, we're going to do res, plus or equal to memo, wait, is, actually, we want to return, we'll return the last element in the, not res, in my memo, usually in my memo. So we want to do memo I, so we're going to compute, yeah, but isn't this, I don't know if this is going to be that much faster, because this is still going to, no, but you have to compute from the base though, so we'll we'll do this. So we'll do memo at I plus or equal to it. We iterate through j. So if I look at my I, so if I was equal to 5, we should get this result. So if I is equal to 5, I think we're going to want to go to 1, 2, n plus 1. So we start, so when I is equal to 1, if that's the case, I need to fill in this one to be 1. But yeah, so if I is equal to 1, then what I'm going to do is iterate through this whole thing, but I need to iterate through the j's. So we need to start, so I need to start, the left side is 0 and then it increments. So j has to increment to I, because, yeah, and then on the left side we have to take memo of j times. So then if I is equal to 5, that's what I'm trying to do. I'm trying to do the example when I, no wait, let's do the example when I is equal to 6. So we're trying to calculate memo 6, assuming we've already calculated all the other memos. So what we need to do is we need to iterate through j, and j needs to go from 0 to 5, right? That way we get 0 to 5 for our left trees, and we need to go the opposite direction for the other one. So we need to do memo, so first off, let me think. What would give me 5 initially? Probably doing I, since I is 6, I have to minus it by 1, because j starts out as 0, and then j will increment until it goes to 5. So 5, yeah, so that could give you 0. Okay, so let's run this code. I think I'm going a little bit fast, but I'm also kind of concerned about how long this video is. Very concerned. Let's see if this will actually work. Hopefully this won't TLE. Okay. Okay, so anyway, so I think I'm pretty much done. Like, I feel like this video has been pretty long. Okay, it's probably 17 minutes in, so I should probably definitely end it. But so at the beginning I did naive recursion. Naive recursion didn't work. It actually TLE'd. But then when you do the memo and you save the subproblems, you don't have to recompute them. That really improves your ability to. That's the only way that this problem even seems to finish. But okay, yeah, I think that's it. So yeah, so going over the pattern was the most important thing. Figuring out this pattern and then figuring out how to code it. Like looking at this example is super helpful here, and figuring out how to code it. So yeah, so thank you for watching.